Okay, so in this video I'm going to talk about the conjugate pairs theorem, but before I discuss the conjugate pairs theorem, what I want to do is talk about how to solve for the zeros of a function, and this example will lead into what the conjugate pairs theorem is. To solve for the zeros of a function, you would set the quadratic equal to 0. This is a quadratic because it has the highest power of 2. It is also a trinomial, meaning that most of you would try to do AM on this. That being said, I will put x and x here. I am multiplying to a positive, so my signs would be the same. And what will they be? Negative. The factors of 5 are 5 and 1. There aren't any other factors. That does not add to negative 4, though. It adds to negative 6. So this is not what I'm going to do to get my zeros. So like I said before in class, math is all about trial and error. So we tried AM, it didn't work, and we're going to do another method. So what we're going to try to do here to solve for the zeros is we are going to use the quadratic formula, which is given to you on your reference sheet. So there is no need to memorize this. So A is equal to 1 here, B is equal to negative 4, and C is equal to 5. I'm going to substitute these values into the quadratic formula and see if I can solve for my zeros. So negative 4 times 1 times 5, all over 2 times 1. What I end up getting here is a positive 4 plus or minus 4 squared is 16, 4 times 5 is 20, all over 2. That becomes 4 plus or minus the square root of negative 4, all over 2. That becomes 4 plus or minus 2i over 2. The reason why I have I is because there's a negative in the radical. And this will reduce to 2 plus or minus I. Now if you notice here, I have two answers. I have x equals 2 plus I and x equals 2 minus I. These answers are conjugates of one another because they have a middle term or middle sign that is different. And that means they are conjugates of one another. Now the conjugate pairs theorem is very important because although my answers are imaginary, meaning they have eyes, or complex, whatever you want to call them, they're not real. Even though they're not real, my answers, my zeros are not real. When I look at my polynomial that I took these answers from, all of the coefficients in my polynomial are real. And the reason why is what I'm going to show you now. So say I was supposed to go backwards, and they gave me the two roots, and they asked for the polynomial. Well, what I would do to get my polynomial is I would bring these back to the x. So minus 2 plus I minus 2 plus I. That would get me x minus 2 minus I for the first set of parentheses, and x minus 2 plus I for the second set. To get my polynomial, I would do box method, and hopefully end up with a polynomial that has no imaginary parts. And that's what the conjugate pair theorem really states. I'm going to have x squared here, negative 2x, negative xi, negative 2x, positive 4, positive 2i, xi, negative 2i, and negative I squared. Now if you notice, the 2i's cancel and the xi's cancel. You are going to be left with x squared, these combine to be negative 4x, plus 4 minus I squared. But the I squared will become a negative 1, becoming positive 1. And that positive 1 will add with the 4 and get my polynomial of x squared minus 4x plus 5. So there you have it. What the conjugate pairs theorem does is it allows you to have a polynomial with real coefficients but with imaginary answers. So if you look at this question, it says write a polynomial function of the least degree, so the lowest degree possible, with integral coefficients, so no imaginary numbers, that has the given zeros. Now they give us x equals negative 1 and x equals 2i. According to the conjugate pairs theorem, if you have 2i, you will have negative 2i. And that is because we want the integral coefficients. And they always work in pairs, just like the example I showed you in the first slide. So what I'm going to do to get my polynomial is add 1, subtract 2i, and add 2i. I end up getting x plus 1 in my first set of parentheses, x minus 2i in my second set, and x plus 2i in my third. To get my polynomial, I'm just going to multiply by using box method or FOIL. And it's very important to do the imaginary parts together first. And that's because if you remember our first slide, they will cancel out the imaginary parts because they are pairs. So this will be x squared, this will be minus 2xi, this will be positive 2xi, and this will be a minus 4i squared. Now that will be x squared. These will cancel because they are opposite signs, and minus 4i squared. Now I squared is equal to negative 1, so this becomes x squared plus 4. I'm not done yet though because I have this x plus 1 piece that I do need to multiply by. So I'm going to do box method one more time to get my final polynomial with integral coefficients, so no imaginary coefficients. So I get x cubed, 4x, x squared, and 4. And my polynomial is x cubed plus x squared plus 4x plus 4. And we always want to give polynomials names, so I'll name it p of x.